Hello, everyone. My name is Tatiana Shavrina, and together with my colleague, Dina Pisarevskaya, we are presenting our work on a bilingual Q&A system with Russian GPT-3. So we are working on the spare devices and Artificial Intelligence Research Institute in Russia. So let's dive in. Long story short, bilingualism and also multilingualism has become a recent trend in NLP models, but most of all, it became, this kind of benchmark to validate new models, right? We have a lot of new cross-lingual and multilingual benchmarks by now, and submitting a new model, a new architecture, well, it definitely requires by now some effort put into multilingual abilities of the architecture. So we have like MT5, we have multilingual BERT, and so on, and a lot of multilingual benchmarks. So making a cross-lingual generalization is a kind of recent task that we obtain quite a decent quality by now. So our work is focusing on the bilingual question answering system for Russian and English. And a lot of works, recent works on the related topic, they show that actually to achieve state-of-the-art results for particular languages, for that kind of task, you should better use not like multilingual model with 100 languages, but you better use a few languages in the training set and maybe like monolingual models fine-tuned on other languages as well. So this is kind of a, tricky result because, of course, the languages are distributed in the training data unequally if we're talking about a large internet corpora. So that kind of makes sense. And our work, focuses for English and Russian, and that's why we use Russian-based GPT-3, which was pre-trained with a corpus of Russian Wikipedia, Russian internet data, and also, English Wikipedia and some parts of the English corpora incorporated in Russian internet eventually. So speaking about multilingualism, this cross-lingual ability to generalize, it gets this additional task-specific value as because of that ability, we can enlarge our knowledge base significantly, right? Because the information that we have in many languages, it just doesn't match in these languages. So what we have in Russian Wikipedia, we cannot have like this quite the same in English and maybe in some other languages. There are pieces of unique information that we have only in one language, and we want to enlarge our knowledge base and be able to generalize over every fact in any language and then use it for question answering task. So this is the point. And what we are doing is eventually we are focusing on the knowledge base for Russian language. And we use the English language as the additional source to, enlarge the information amount that we have for question answering tasks. So for that purpose, we're using the bilingual approach for model fine tuning. And we use like standard data sets. That's Squad for English, and its analog, Spur Squad for Russian. They're quite the same with comparable amounts of paragraphs, questions, and answers. And we also use machine translation data. So we get the original paragraph in English and the question and the answer, and we translate it with Helsinki NLP to Russian. And vice versa, the Russian data is translated to English. So then we have matching paragraphs, questions, and answers and we can switch, the language and try to fine tune the model to give us the answers from the paragraph in another language. So that's the point. So the fine-tuning setup that we use is quite the same. So we have some special tokens, special token of the beginning of the sequence, the end of the sequence, and the language. And the special token of the language indicates in which language we want the answer. And it doesn't indicate in which language we have the paragraph, so we can have the paragraph in English or in Russian, and we can indicate whether we want the answer to be in English or in Russian, not looking at the paragraph, so if we ask to extract the Russian-based answer from the English paragraph, then our model should generalize and somehow extract and translate the answer. That's the point. So we use quite the standard hyperparameter setup for fine-tuning the model. Getting all the data, we have used the standard train and development sets split on the Sber squad and squad data sets. So we have 4 setups, Russian, from English to Russian, from Russian to English, and from English to English. And then shuffled all the examples. We have about 150,000 training formatting lines. So after that, we train the ruGPT-3 XL model. So it's 1,300,000 parameters. Yeah. And we tested on the standard dev sets in various languages. So we have 4 setups for validating. So these are hyperparameters for fine tuning. So we have like 20,000 steps for tuning, standard amount of iterations, and so on. So what we have as an example of such an interesting fine-tuning. So this is the example that I got, like this is the paragraph in English, and we indicate the special token that we want the answer in Russian. The question is in Russian, and what we got from the model is eventually a correct answer, which doesn't match exactly the golden answer. So we have the text about the monetary policy of Canada eventually, and the question is like what amount of times goes by from, defining the monetary policy to its bringing to life. And the answer is like from 18 to 24 months. And it cannot be like found exactly in the text. It can be extracted in another language, and that's why we have a translation, which is like absolutely correct. But from the points of exact match and standard metrics for question answering, it's not very good. So what should we do then? Like if we are, solving the question answering task with generative architectures, and GPT-3 is a generative architecture, that's a decoder eventually. So what metrics can we use? And speaking about the quality, there are a lot of questions, and I'd like to pass the mic to my colleague, Dina, who will tell you about the metrics that we used.
Thank you, Tatiana. My name is Dina, and now I'm going to tell you about model evaluation. So we have 4 setups. English, Russian, it means that question, gold, and generated answers are in Russian, and text is in English. Russian, English, question and both answers in English and text in Russian. Russian, Russian, question, both answers and text in Russian. And English, English, question, both answers and text in English. And we apply 2 types of metrics. It means classical strict metrics such as exact match, ruGPT or Meteor, and fuzzy metrics for different aspects to estimate if a generated answer is relevant. Next slide, please. And here you can see our table with metrics. Later, I'm going to describe the main takeaways. Next slide, please. As to classical strict metrics, Russian setup yields the highest exact match values between gold answer and generated answer. And both cross-lingual setups provide better results than the simple English setup. As we see, ruGPT-L and Meteor metrics also show the same patterns. It is also worth mentioning that among string matching metrics, exact match has the lowest scores. And it means that generated answers, especially for English and cross-lingual setups, may be not presented as an exact citation from the paragraph. That's why we also use less strict fuzzy string matching metrics. Next slide, please. Here, Russian setup also demonstrates the highest results for matching gold answer and generated answer using Levenshtein distance. It is fuzzy Russia in table. Cross-lingual setups have better scores than English setup. And the same also concerns the fuzzy lemmas intersection metric with thresholds over 70%. We also measured a special Cassin distance between gold answers and generated answers using sentence BERT. And if we compare results for English and Russian English setups, we see that English results are lower than cross-lingual Russian English results, as in other metrics that we already mentioned. And we tried a variety of thresholds, and this option remains with more strict and less strict thresholds. And next slide, please. And finally, we implemented fuzzy metrics based on named entities intersection in gold answers and generated answers. We found out that named entities were extracted, using Natasha Python package, and we estimated named entities ratio for the whole development set. And in addition, we also measured more stricter precision only for generated examples with named entities. It means that an example was considered as true positive if minimum one named entity from the generated answer was presented in the gold answer, and the whole number of examples with named entities in generated answers was considered as true positives and false positives together. And as in other metrics, Russian setup yields the best results. But it was also interesting that, in contrary to other metrics, English setup results for named entities precision are better than cross-lingual setup results. The next point is what about our baseline and its evaluation? And thank you, Tatiana. And now we're going to the next part.
Yeah, thank you so much. So speaking about the baselines, as the setup is kind of original, we should compare our model, of course, with something similar or more standard. And so we have used the monolingual Russian BERT, as there are like a few models that can be used in that kind of setup. You know, we need a kind of monolingual model that has seen some parts of the English data. There are not many models like this, but the Russian BERT model from Deep Pavlov repository is actually quite like this. So we have used it in the same setup with the same fine-tuning formatting, with a simple transformers pipeline for fine-tuning the model with quite the same data. And what we got in the same metrics is kind of a tricky result, because in this pipeline, BERT tries to extract, always extract the answer from the text, and it cannot extract the correct answer from the text if it's in another language. So eventually the BERT model fine-tuned gives us the results in the original language of the paragraph, even if the special token is indicating that the language should be in another, we should use another language. So the same paragraph about the monetary policy of Canada, and we have the same question, and the golden answer about, the credit conditions is in Russian, but the answer of the model is in English, and it can be extracted from the paragraph exactly. So evaluating the baseline with our metrics, we see that somehow we have, you know, decent results in monolingual conditions, Russian and English-Russian, with English being like worse, but not at all we have, you know, any cross-lingual abilities. So we have like much less cross-linguality than we have in the case of Russian GPT-3 eventually. And why does that happen, you know? So speaking about this kind of metrics and approach with generative models to question answering, we should explore, you know, the results. So there could be like two possibilities of the interpretation that we have come up with. First of all, the GPT-3 model learns to translate texts from one language to another, and this is exactly what we want, right? We want to generalize over data in two languages and work best for one specific language, for Russian in particular. And the other interpretation can be that it just learned somehow to compare two versions of the Wikipedias, as it's possible that it has seen, like, you know, the corresponding articles from the Russian Wikipedia and from English Wikipedia, and somehow they correlate. So there, that were the hypothesis. And so to test that, we have used a non-wiki paragraphs in various languages. So this is the news text in Russian that hasn't been in the training setup. It's very different in genre. In the language that is used, and the question is in English, and the special token requires that the answer would be in English. And so eventually what we have is that ruGPT-3 gives us the correct answer in English, which is like quite the same as the gold answer, you know. So, and this is what we don't have with the BERT model. So with BERT model, we'll still have the correct answer, but it's in Russian, not in English. So somehow, you know, kind of interesting results for us is that, you know, the decoder model is enough to create somehow the task-specific machine translation. And I suppose that the results that we got for Russian and for English are quite decent. They're not, of course, state-of-the-art, speaking in the standard metrics, you know, exact match for squad or per squad. Of course, they're not state-of-the-art. Still, they're quite decent. And in this setup, it's proven that we can use, from the point of engineering approach, we can use these models to enlarge our knowledge base when we know when, you know, other QA model like cannot give us the answer. For example, we can address the sources in other languages and it would be working somehow. That would be much better than nothing. And for example, Russian setup, we have the best results. Of course, we have like 83% of corresponding named entities in the correct answers. And for English, it's 52% of correct answers speaking about the named entities. But also in cross-lingual setup, we have quite decent results. Like from Russian to English, it's 51% of correct answers in terms of named entities, and also from English to Russian, it's like 75% of correct answers speaking of named entities mentioned in the answers. So our models and the code are open source, and we will be happy to receive any feedback from you. Thank you so much. And we will be happy to answer the questions and any comments. Thank you.